Hello friends and welcome to this video. We are going to address the topic that it is titled Normalized LMS Algorithm from chapter 6 titled as Adaptive Filters while learning the subject Advanced Digital Signal Processing. The two algorithms, the steepest descent algorithm and the LMS algorithm we have seen. The LMS algorithm is more popular than the steepest descent algorithm. The differences already we have seen thereupon. And now after completion of the understanding for the convergence of the LMS algorithm, we are going to discuss the another version for the practical applications here, and this is called as the normalized LMS algorithm. So while having the design and implementation of the LMS adaptive filter, there is one difficulty along with others also, but it is of more concern here. So the difficulty in this design and implementation is the selection of the step size that we have denoted by small mu in the earlier mathematical equations here. So now if it is the case of the stationary processes here, the LMS algorithm converges into the mean if mu, that is the step size, is greater than that of the 0 but less than 2 divided by lambda suffix max, and it converges into the mean square if it is greater than 0 but it is less than 2 divided by TR of the autocorrelation matrix denoted by capital R suffix x here. Now since capital R suffix x is generally unknown here, either lambda suffix max or the autocorrelation matrix capital R suffix x must be estimated in order to use these bounds. So here we have one way around this particular difficulty is to make the use of the fact that for the stationary random processes, the TR of the autocorrelation matrix R suffix x is equal to p plus 1 multiplied to the estimate of mod square of x of n. So therefore the condition for the mean square convergence can be replaced with the representation mu greater than 0 but less than 2 divided by, here in the denominator we have p plus 1 multiplied to the estimate of mod square of x of n here. So here estimate of mod square of x of n is the power in the input discrete time random process denoted by x of n here, and this power may be estimated using the time average such as given by the estimated version denoted with the help of the cap over the head of capital E for mod square of x of n. This is equal to 1 upon p plus 1 multiplied to the summation k is equal to 0 to small p for mod square of x of n minus k. That leads to the bound on the step size for the mean square convergence. This bound is represented as mu greater than 0 but less than 2 divided by Hermitian of x of n into x of n here. Now one convenient way to incorporate this particular limit or the bound into the LMS adaptive filter is to make the use of a step size given by the form mu of n, that is equal to beta divided by the Hermitian of x of n multiplied to x of n. We can also represent it as beta divided by the square of x of n in this representation. So in this representation, beta is the normalized step size having the range that is greater than 0 but less than 2. Now if we replace mu into the LMS weight vector update equation with mu of n, leading to a normalized LMS algorithm that we can abbreviate as capital NLMS. So this can be given by the mathematical equation w suffix n plus 1, that is equal to w suffix n added by beta into the ratio where numerator is the complex conjugate of x of n and the denominator is here the square of double mod of x of n, and this ratio is further multiplied to small e of n. Now here we have to note one point, that the effect of the normalization by the factor into the denominator, that it is square of the double mod of x of n, is to make alteration of the magnitude but not the direction here, and this is of the estimated gradient vector for the magnitude and the direction here. So therefore, with the appropriate set of the statistical assumptions, it can be shown that the normalized LMS algorithm will converge into the mean square if we have beta greater than 0 but less than 2 set of 4, 34. Now in the LMS algorithm, the correction that is applied to the weight factor W suffix n is proportional to the input vector x of n. So therefore, when x of n is large enough, the LMS algorithm will experience a problem with the gradient noise amplification, and with the normalization of the LMS step size by the square of double mod of x of n in the normalized LMS algorithm, this noise amplification problem is diminished here. And although the normalized LMS algorithm bypassed the problem of noise amplification, we are now faced with a similar problem that occurs when double mod of x of n will become very small. So the alternative representation will be having the use of a modification to the normalized LMS algorithm. This modified version is represented as W suffix n plus 1 is equal to W suffix n added by beta multiplied to the complex conjugate of x of n divided by epsilon added to the square of double mod of x of n into the e of n to multiplication to this particular ratio. Now here it is one new factor introduced in this current representation, that it is denoted by epsilon, and this is some small positive number here. Now compared to the original LMS algorithm, the normalized LMS algorithm requires the additional computation to evaluate the normalization term. So however, if this term is evaluated into the recursive fashion, so that time we have the square of double mod of x of n plus 1, that is equal to square of double mod of x of n added by mod square x of n minus 1 n plus 1 minus mod square of x of n minus p. So that time the extra computation will involve only the two squaring operations, one addition and one subtraction here. So this was our topic, the normalized LMS algorithm here. So we shall continue into the same chapter with the next lecture, possibly addressing the MATLAB demonstration for the normalized version of the LMS algorithm, and then we shall address one of the application of this type of the adaptive filtering. Possibly we shall take the application to be for noise cancellation here. Thank you.